The next talk will be given by Johan Peltenburg from Delft University on the subject an accelerator for Posit arithmetic targeting Posit level 1 BLAS routines and per HMM.
All right. Yeah. So thank you for having us here. My name is Johan Peltenburg. A little disclaimer. Or credits, let's say. So most of the work that I'll present is actually based on work from one of our master's students, Laurens van Dam. And his master thesis is available online, containing even more information than the paper he wrote out of this. So the work was done at the Computer Engineering Lab in TU Delft. But special thanks goes to Jin-Ho Lee at IBM, who spent many hours with Laurens doing lots of debugging over a transatlantic connection, let's say. So the outline for this talk is we'll take a look at some Posit, an implementation of Posit arithmetic in hardware. We're also using the quire register that is in the specification. So then we'll move on to use that Posit arithmetic in two applications. So one of the applications is a Posit vector arithmetic accelerator, and another application is a pair hidden Markov model accelerator that we had lying around. We were able to drop in and replace the floating point arithmetic almost very smoothly using the Posit arithmetic hardware that we created. And so it was interesting in that accelerator to see what the effect on the accuracy would be. So this is an application that is used in bioinformatics. All right, so let's take a look. I think, by all means, I'm not as experienced with the posits as Laurens was, but I think from the tutorial yesterday, we've all seen very well how the number format works. So I won't go over this too much. Yeah, so in hardware design, yeah, we do need to take into account all these fields, of course. And the first thing we do before we can start an operation is to extract all the fields. So the Posit arithmetic in hardware that Laurens built is built up over 3 stages. So depending on the operation, we need one or more numbers, Posit numbers. So first, all the fields are extracted. We only have 2 special cases where it's not a real or where it's 0. But other than that, all the Posit fields are extracted. I think in the previous presentation we've also seen a few tricks on how to do that. Then we could move on to the actual operation. And when we do a bunch of operations here, we keep the unrounded fraction for intermediate results. So this is an implementation of the quire register that's also in the specification. And then at the end, we normalize the Posit. So I can now skip over this. So let's first look at the extractor. So all the fields are obtained. We have to detect the size of the regime by counting the leading zeros or ones. We shift the fields accordingly, and the 2 special cases create these control signals in 0 and not a real actually that we can use in the control mechanism in the rest of the accelerator. So in the second stage, we can do all sorts of arithmetic. So we implemented 2 operations, an adder and a multiplier, and they're both fully pipelined. So for the adder, we can take a 4 or 8 stage pipelined adder. Of course, if you take a 4-stage pipelined adder, we might have a bit longer critical path. And depending on the technology, the clock frequency could be a little bit lower than the 8-stage pipelined adder. And the multiplier is also pipelined with 4 stages. So this is the interface of that unit. So finally, we have the accumulator, and without rounding, we keep accumulating some input, and we feed back the unrounded fraction to another. Finally, we can get the accumulative result out of there. So after doing accumulation, we can have a very long acquire register that we have to pack back into a normal Posit. But we still want to retain this control information if we do additional operations after this that we might just skip because things are 0 or not a real. So the rounding scheme that's being used here is round to nearest and tied to even. So let's move on to the accelerators that we did. So the first one is a relatively simple one. This is for Posit vector arithmetic. We did BLAS level 1, so basically linear algebra subprograms level 1. So that's vector addition, subtraction, and multiplication, element-wise. So we also have the dot product using the wide accumulator, and we finally also have an element-wise sum between two vectors. So these are mainly optimized for performance and decimal accuracy because of the use of the acquire.
Vector addition is element-wise. Vector sum is the sum of all the elements into a scalar.
Right, yeah. Did I say element-wise twice?
Yeah.
I think I caught myself doing that. Sorry. Yeah. So, but that's correct.
And you're doing vector sum with acquire, aren't you?
Yeah. So the vector sum does include the acquire, yes. Yeah. Yeah. So actually, in the implementation, we just make the second vector a vector of all ones, and then use a dot product.
While you're interrupted, you didn't mention which procedure you're working with.
Okay, so all of the, I'll get to that. So all of the posits we use are 32-bit posits, and we implemented two ES sizes. So we used ES2 and ES3. All right. So one of the things I think that is quite important for us to do is because we're working on this in the group as well, is that you can build this accelerator, and it's nice if it works. If it interfaces with one language, but it's even nicer if it can interface with many languages. So some programming languages, they box numbers into objects. So for example, Python and R do this. That sort of adds a lot of overhead in the interface to the FPGA, and there's lots of information in the memory that we don't actually use to do the calculations. So, for example, in Python, this is solved by using NumPy, which is just a C backend, basically. Now, luckily, there's this Apache project called Arrow, and it's sort of it defines an in-memory data format for all sorts of data types. And it has a cross-language support. So rather than coming up with serializers for boxed representations of posits and potential boxed representations of posits in all of these higher level languages, we decided to use Apache Arrow as a common data layer. And this way, from all of these languages that we have here, we can with quite good throughput move posit vectors over to the Posit accelerator, enabling this acceleration for all of the languages. So the BLAS accelerator. So the schematic overview would be we use Arrow to represent the two input vectors as two Arrow arrays, and then depending on the operation that we do, we get either one output vector. So if we do element-wise addition or multiplication. Or we get one posit, so if we do the element sum over all the elements in one vector, or if we do the dot product. So this is what the hardware looks like. So we implemented this on a Xilinx KU60 FPGA. That's a Kintex device, ultra scale. The interface we used to the host was a CAPI interface. This is available on a Power 8, also on a Power 9 nowadays. So assuming that these vectors are stored in the Apache Arrow format, then we use this framework that we are developing in our group called Fletcher, and it generates the hardware interfaces for these vectors. Now, after some initial buffering, we use all the aforementioned components to do all the operations. So we extract the posits, then we multiply them, accumulate them, aggregate them because there's some parallelism being exploited in there. And then finally we get the result. So if it's a vector, we also have this thing called a column writer that writes back an array that we can read in all those languages again. Or we just write, or we just give a single result back as in a register that we can read out from the host. It's not working anymore. Oh, it is now. Okay. All right. So we'd be interested, of course, in a couple of things. So one thing is speed over emulation library. So the Stillwater SC library was used. Initially with a more naive approach of doing the vector operations. So we get, of course, crazy speedups. So you can see initially we pay a lot of overhead to boot up to initialize the FPGA registers and transfer the data, especially when the vector links are small. But at some point, of course, we will just that latency is not very important anymore in the total time, and then we start to get very good speed up. So we're about 4 orders of magnitude faster than the emulation library if you do the vector operations more naively. So we get about over 100 megapops. So that's megaposit operations per second. That's quite useful, I would say. So if we use some more advanced BLAS libraries in the multi-threaded mode, using eight threads. So this was done on the software measurements here are done on an Intel machine with 8 threads. Then the software speeds up, but still, the hardware accelerator vastly outperforms the software emulation. So that's kind of nice. We think that's useful because a lot of algorithms, we can express through vector and matrix operations. Now let's take a look at the accuracy. So what is the increase in accuracy? So depending on the vector length, we see that generally the decimal accuracy of the floats goes a bit down. So it does for the posits. So for software emulation, we see that it's about 1 decimal point better in general. But because we use the quire, the 512 bits quire for the 32-bit posits, we get a pretty good decimal accuracy even compared to the software emulation where we don't use the quire. So to summarize this accelerator, it's a modular design, the units are very modular. We could almost drop and replace the float units. Unless you want to use a quire register, you have to do a little bit more work. We get very good speed ups, of course, and we get also some improved decimal accuracy. So we'll move on to the next accelerator. So this accelerator is used in genomics, so in bioinformatics. So the pair-HMM model is used in pairwise sequence alignment. So first there's millions of tiny reads that are taken by a big machine from a sample of DNA, and these are compared to a reference genome. So after some initial alignment step, there's actually also a wish to calculate the probability that these alignments are correct, what they call the likelihood. And this is a pretty big step in the whole pipeline. So there's a few well-known genomics analysis platforms, for example, G80K, and these implement these sorts of calculations. So in general, you have two sequences of DNA information, and what could happen is there could actually be an insertion compared to the other sequence in one of them, or a deletion, or it could be in a match. And with each of these and some additional information that is based on a lot of information coming from the initial alignment, we can calculate the likelihood of this match being correct. And so there's a whole Markov model related to that. So FPGA accelerators are especially good in doing these calculations. So we already have very good speed-ups, even when we do this with many threads on a CPU. And that's because the algorithm has a specific way of calculating it. If you look at all the different combinations that you could do, you could put that in a matrix, and then you could traverse. You could iterate over the elements in the matrix in an anti-diagonal fashion. So there are some dependencies amongst the calculations that point to the top left, to the left, and to the top for each cell. So we can traverse through the matrix over the anti-diagonal in parallel, and we usually implement this way of going through the matrix in a systolic array. So the specific algorithm that does this is called the Perturbation algorithm. It sparks our interest because, so first of all, we already had this accelerator lying around in our group. It was pretty fast. For a while, the fastest you could get. Another thing is the bioinformaticians, they value the accuracy quite a lot. So so much actually that, well, they also value speed, right? So they make a little trade-off that's quite interesting, I think, especially for a conference like this. So the thing is that they do a lot of their calculations in float 32. So they just get some higher throughput than float 64. But if they see that, oh, well, actually the result is in an array that's quite inaccurate, they redo these calculations again. Now, sometimes there are some timing critical applications for the genomics analysis pipeline. So they could be used in hospitals, and maybe if there's some, some need to do them fast, you don't want to redo calculations necessarily. So it was sort of interesting for us to see, in combination with this application, what the posits would do. So we did an analysis of what sort of the extra decimal accuracy we would get from the posits. So I think, especially yesterday, we've already seen a few nice slides explaining that if we scale them properly, we get into a range where we have more bits for the fraction field, and then we can obtain a higher accuracy. So after a while, that doesn't make sense anymore, and we just lose accuracy actually compared to float. For float, the fields are fixed, so we can't really do that there. A similar top-level architecture exists for the Perturbation accelerator. We also use, again, the same framework I was talking about, so we can integrate it with many programming languages quite easily while retaining a lot of bandwidth to the accelerator. And so everything gets read from these column readers that are generated based on the data format, and gets fed into this systolic array implementation that I was talking about. So that looks something like this. We stream in the reads from this side. We stream in the haplotype from the top. And these processing elements, they each calculate for one matrix element the desired output. So they do this in a pipeline fashion. I believe for this implementation, they take 16 cycles. And the interesting thing is, in the end, there is an accumulator to sum up a lot of values. So this is also a property of the algorithm as well. And for this accumulator, we also use the increased precision quire register. So if we look inside a PE, it's quite an elaborate calculation. So internally, we do not really use that quire register just for the final accumulation. And we have about 4. The longest data path here contains about 4 of these Posit operations. So there's quite a lot of logic inside each processing element. So we can look at the performance. So here's some speed up, but do note that there's a little times 10 to the power 5 there. We already have a lot of, just because of the fact that the systolic array very well captures the data flow much better than a CPU bounded by a control pad could ever do. So we already get a lot of speed up from that. And actually the speed up that we get here is only magnified by the fact that we don't have to use emulation, of course. So they're crazy speed ups, but they're true. We can take a look at the different haplotype lengths. And the longer we make this thing, so the haplotype is one of the sequences. So the longer we make this thing, the better the performance gets. So here the different colors are the other sequence length. So they don't necessarily have to be the same length. For example, they can stop or start early. They can stop earlier depending on either of them. But this one is always longer than the other one, so that's why you don't see the purple and green dots there. So what about the decimal accuracy? So we also used the 3-bit ES field, but the results are quite similar for this algorithm. So it's a little bit convoluted, but the float is generally this little star. They're pretty much at the bottom, and we can see sort of on average we get about a 1 decimal point more accuracy from the pairage from doing the work with posits. Now, what sort of impact that would have on the grand scheme of things in the GATK pipeline, we'd have to ask bioinformaticians, because they're really picky about these sorts of things, and they might have a lot of things to say about this. So that would be interesting to follow up. So to summarize this accelerator, we have done this accelerator implementation with the posits. Very useful that we can almost drop and replace our floating point units with the posit units that Laurens built. We get very good speed ups. I think some number sort of got lost there. We get on average we get about 0.75 decimals of extra accuracy over floats, and 0.5 over the software emulation libraries without the quire. All right, so to conclude this presentation, we have created the design and implementation of pipeline posit adders and multipliers targeting FPGA. We can use them as a drop-in replacement for any designs that use float units currently. Again, except when you want to use a quire, you have to do some extra work. So we have a high accuracy accumulator. We applied it in 2 accelerators, the vector arithmetic accelerator that you could sort of use for all sorts of applications, probably from all sorts of languages. Because we have this integration with Apache Arrow. We did it for the PairHMM accelerator. For both we see increased accuracy, so that's very nice. Well, obviously we're orders of magnitude faster than the CPU emulation. And I think for a while, if you need high pops, you have no choice but to embrace FPGA accelerators. So in that sense, we'll be interesting. We're very interested to hear all the applications here. And it would be nice to find some nice collaborations there. Bunch of references, and that was about it. So thank you.
So, thank you very much for your talk. I think we have time for a couple of questions.
Thank you. The first question was, I think it was on slide 30. I have two questions on this slide, actually. It was a bit fast, but I think you can do all the accumulations in principle in the quire, right?
Yeah.
Even the last... No, because you multiply...
Yeah, so there...
Could you, in principle, replace all these pluses with something in a quire? That's the question.
Yeah, so the thing is, you know, we have a little bit of an area constraint here. So if you would do that, you'd need quite a lot more space, right? And the thing is, you know, we want to have as many of these systolic arrays operating in parallel in the FPGA implementation as possible. So I suppose it would be sort of a trade-off against accuracy there. I think that is the reason why it's not being used internally, but only in that final accumulating step. Yeah, so you have to think about, you know, I don't know for this accelerator, but a previous one we did based on this work, we could do about 100 of these PEs, right? So you can imagine how much extra area it would take for each of these PEs to do all the calculations with the quire. Okay. That would be a lot of area.
Okay. That was my second question. How many Posit operators do you pack in your FPGA eventually?
So I know for this implementation that there were 16 PEs being used, and I think it's about 17 operations if I am correct here. And then you also have to add the accumulator at the end. That's also an adder and a multiplier.
Okay, other questions? Mm-hmm. So maybe one more question. Right. You have BLAS 1 routines. That was the first part of your talk. Do you have plans for BLAS 2 and BLAS 3? Because that's the high performance thing which you need for matrix operations and so on. Yeah.
So the good thing is that, you know, it fits the fact that we can also use a fixed width type of 32 bits, and the fact that we can sort of drop and replace it with existing units is interesting. We have a few people in our group working on sparse matrix multiplication. So they have all sorts of tools, and you know, based on what I've seen so far in this conference today, and in the amount of interest that there is in posits, I'm pretty sure that it won't take long before we get somebody working on that as well. Yeah. So and then of course the nice thing is that if we do this through Apache, by using the Apache arrow format, we unlock that acceleration power for, you know, all sorts of languages that people might want to prefer to use. Mm-hmm. Yeah. So I would say yes, there are plans.
Thank you very much. Yeah, let's thank the speaker again.